Hello, this is Dr. Muhammad, and I'm going to talk today about the method of least work, and I'm going to give some introduction first regarding this method. So first of all, let's go to the main concept itself, which is related to the least work method. In this method, the compatibility equations are established by using a principle called Castigliano's second theorem, instead of by deflection superposition as in the method of consistent deformation. As you know, that in indeterminate structure in general, we need to use compatibility equations as additional equation to our system or to the equilibrium equation in order to solve our system, right? So in the consistent deformation method, we used the deflection superposition concept in general. But here in the least square or the least work method, we are going to use this principle, which is Castigliano's second theorem, and I'm going to talk about it shortly, so do not worry about it. Okay. With this exception, we can say that both are the same. So the consistent deformation and the least work method, they are the same. The two methods are similar and require essentially the same amount of computational effort. So they are the same, no problem with them. But this is considered only difference in the way itself for composing the compatibility equations. Now let's talk about the advantage of this method. The method of least work usually proves to be more convenient for analyzing composite structures that contain both axial force members and flexural members. Yes, and this is an important issue. Whenever that we are dealing with systems that is containing, if we say that we have a system like a beam and this is distributed load upon it, and it is like linked with a link here, okay, this system is composing of two main elements and totally different elements. The first one is the beam itself, which is controlled by flexural straining actions. So we are going to have beam moments here. However, for this link, it is controlled by axial forces. This means that this kind of system or such a system is very nice to be an application for the method of least work. So it fits well the least work method. Okay, so this is the main advantage of the least work method, that for systems combining or containing axial straining actions member and flexural straining action members, it works well for it. Okay, what is the main disadvantage here? The main disadvantage is it is not general as the method of consistent deformation. So what is the meaning of the word general here? This means that there are some cases where that we cannot apply this method as the case of the consistent deformation. For example, if we're talking about support settlements, temperature changes, and fabrication errors, they are considered to be three different methods, three different applications that is not suitable for the method of least work. It is not suitable for the method of least work. Okay, so this is considered to be the main disadvantage of our method. Okay, now let's go to the next part. Now we're going to talk about the Castigliano's second theorem. Okay, let's talk about this theorem and let's understand it more. Let's start with that we have a beam. Suppose that we have a beam, as you can see. It is two spans, and it is loaded with a distributed load, external distributed load with intensity W. And we have, as you can see, we have like 1, 2 reactions here, one reaction here, and another reaction here. So we are four unknowns for us. So this means that we are having like 4 unknowns and we have 3 equilibrium equations. This means that our system is once statically indeterminate. Let's assume that we are going to take this vertical reaction here, which is By let's assume that this By at the interior support B, let's assume it to be our redundant. Is going to be our redundant because we have only once statically undeterminate system, means that we need only one redundant to work on it. By treating the redundant as an unknown load applied to the beam along with the prescribed loading W, so we're going to deal with it in a very similar way as we have done in the consistent deformation method. We're going to assume that this beam is going to be applied, or as if there is a redundant is going to be applied on the system, and we are going to remove this this support, right? The same point. But here we are going to use the concept of Castigliano's to understand what we are talking about or what we are going to do. An expression for strain energy, we're going to tackle the problem from the strain energy point of view. Okay? The strain energy of this system, which is U, can be written as a function of the external loading, which is W here, and the redundant, which is going to be chosen here, which is By. Okay, so there is a kind of equation that is going to give us the strain energy in the system as a function of the external loading and the redundant that we are dealing with, Okay, so this function or this equation indicates symbolically that the strain energy for the beam is expressed as a function of the known external load W and the unknown redundant By. Okay, so we do not know exactly what is the function, what this function looks like, right? We have no idea now, but we are sure that this strain energy is function of these two things. You can recall the structure analysis one. Already I have explained something similar to this before, and you can find it chapter 7, I guess, and the book of Aslam Kasamali. So I already explained about the concept of the strain energy and Castigliano's in the structure analysis 1. Okay, so you can revisit the videos for this. Anyway, we're going to touch only on the main concept. We're not going into the details of it. Okay. Now, according to Castigliano's second theorem, here this is the point: the partial derivative of the strain energy with respect to a force, which is our redundant, equals to the deflection of the point of application of the force along its line of action. This means that here we are talking about the deflection at this point. Okay. If we are going to take the partial derivative of the strain energy with respect to our redundant that we are talking about, it should equal to the deflection at this point due to the reaction or due to this redundant, right? So this is the main concept of the strain energy or the concept of the least work, that the partial derivative of the strain energy with respect to the redundant should equal to the deflection. Okay, in our case, the deflection here is roller. This means that the deflection is 0, right? That's the point. Okay, so I'm going to read it again to understand it clearly. According to Castigliano's second theorem, the partial derivative, we're talking about partial derivative because maybe the strain equation would reach, it could contain different unknowns, a number of redundant. So we are going to talk about the partial derivative of the strain energy with respect to a force, which is the redundant, equals to the deflection at this point, okay, the point of the application of the force. Okay, that's what we are. Since the deflection at the point of application of the redundant By is 0, by applying Castigliano's second theorem, we're going to reach to, to this equation. And this equation, it represents the compatibility equation in the direction of the redundant By. This is what we call it, the compatibility equation. This one is the compatibility equation in the direction of redundant By. And it can be solved for the redundant. We can solve it for the redundant. So it is one equation in one unknown, which is By, as we are going to see later. Okay. Now let's understand what is the meaning of the principle of least work. Now previously we have explained the meaning of Castigliano's second theorem, and now we're going to talk about the principle of least work. The principle of least work is telling this: as the equation indicates, the first partial derivative of the strain energy with respect to the redundant must be to zero, must equal to zero. As you can see here, we didn't say anything. It is the same as we said before. This implies that for the value of the redundant, which is By, that satisfies the equations of equilibrium and compatibility, so we need to satisfy two things here, equilibrium and compatibility, the strain energy of the structure is a minimum or maximum. Because assume it as a function, u is considered to be a function of By, as we said. It is function of By, and w, which is the external load, it's constant, so no problem here, we can remove it. But anyway, let's put it like this. This is a function. If we are going to say that this function, the derivative of this function with respect to the main variable here, which is By, partial u, partial By, equal to 0, this means what? Yes, it seems to be something like this. It could be minimum, or it could be maximum, right? Because partial u, partial By, it means the slope of the function. This is considered to be u, which is the strain function or the strain energy. So it could be something like this, or it could be something like this, and we are whether in the minimum region or the maximum region. This equation tells us that the slope of the function is 0, so we're not sure. Okay? Since for a linearly elastic structure, we are talking about what? Linearly elastic. This is the condition. We are under linearly elastic case. There is no maximum value of strain energy. We're not talking about this case. In linear elastic, we are talking about, because it can be increased indefinitely by increasing the value of the redundant. For example, if we are going to increase the redundant, then the value, this value is going to be increased over and over and over again. But whenever that we minimize, whenever we are talking about minimization, what is the minimum value of By? That the strain energy is going to be 0, where that the deflection is going to be 0, okay? Then this is our case. This is the case of the least work. So now let's repeat it. Since for the linearly elastic structure, there is no maximum value of strain energy, because it can be increased indefinitely by increasing the value of the redundant, we conclude that for the true value of the redundant, the strain energy must be, yes, minimum. The strain energy required to maintain the point of the application of the redundant, which is By, this deflection needs to be 0 because the strain energy is minimum. This conclusion is known as the principle of least work. And if you want to have more explanation about this, you can revisit, as I said, chapter 7 or the previous videos that I uploaded to the iCampus regarding the concept of least work. Okay. Now let's state it and put it clearly so that we do not forget it. The magnitudes of the redundance of a statically indeterminate structure must be such that the strain energy stored in the structure is a minimum. The internal work done is the least. That's the meaning here. Okay. Okay, this is only a theory that we need to understand only once and keep it in our mind, and then we are going to apply it through our examples. Okay. If we have, what if that we have multiple, or it is the indeterminacy of the system is not only one, it is we have multiple redundants, R1, R2, R3, and R4, and so on. In this case, we are going to say that the least work for in redundance as the partial derivative of the strain energy with respect to R1, which is redundant number 1, should equal to 0. And this would be equation number 1. And then we're going to apply the same concept for redundant number 2. And this is equation number 2. And so on and so forth until we reach to Rn, which is going to make our n equations. Okay? So this is considered to be, this represents a system of n simultaneous equations in terms of n redundance and can be solved for the redundance. These are the equations. Each equation has only one unknown. Then we can solve for this unknown, and this is another unknown, and this is another unknown, and so on. Okay, so this is the advantage of least work, that we can separately make our concept or our equation for each redundant separately, and we can get the redundant easily. Okay, so this emphasizes the meaning of the simplicity and advantage of the method of least work. Okay, now let's go to some examples to understand it. Okay, let's go to some examples to understand what we are going to do. Okay, let's go with this example, which is 14.4 in our textbook. Determine the reactions for the beam shown by the method of least work. Let's have a look on this beam. We have a cantilever here, we have a fixation here which has three components, AY, AX, MY, so we have three redundant. And here we have a roller which have only one redundant. Okay, so we are dealing with 4 unknowns. Our system generates, so we are having four unknowns, and we have 3 equilibrium equations. This means that our system is once statically indeterminate. The distributed load here is 1.6 kips per foot. The distance is 330 feet from A to B. We have EI is constant across or along this beam. We are going to talk about this X shortly because we are going to choose our redundant to be BY. Okay, so now let's go and understand it more. The beam is supported by 4 reactions, so its degree of indeterminacy equals to what? 1, as I said. The vertical reaction, BY, okay, at this here, BY, and the roller support is selected as a redundant. You can select any reaction among the 4, but we have selected this redundant or BY to make it easy for us, okay, in order to make it easy for us. We will evaluate the magnitude of the redundant by minimizing the strain energy of the beam with respect to BY. Okay, this is what we are going to do actually. We're going to say that partial U, partial BY is equal to 0, right? Right. First of all, we do not know what is the meaning of the strain energy and how we can connect it with BY. This means that we need the strain energy first to be a function and in the function of BY, and then we can make the partial derivative, right? Okay, that's what we are going to do now. For flexural element, we have a formula for the strain energy in terms of the moment. So whenever we are talking about flexural members, okay, we are talking about the main straining action controlling is the moment. This means that we need to get this u, which is the strain energy, as a function of moment. And this moment, which is going to be at any point across or along this beam, should be defined by our main redundant, which is By. Okay, so we have strain energy. The strain energy in this equation of the least work, we're going to make the partial derivative with respect to By equated to 0. This u, which is the strain energy, need to be function of m, which is any moment along this beam, and this m should be a function of By as well. Okay, now let's assume that we are going to take this B to be our origin, and at any point here we can describe, or we can locate it as relative to this point origin, which is B, with parameter x. Now let's go to this. The strain energy of a beam subjected only to bending, we're talking about bending here, moment, okay? Because the beam, why we are talking about bending here? Because beam is controlled by flexural straining action. So bending is the main parameter that we should consider, okay? So can be considered as you can see here, u, which is the strain energy, equals to the integration, limited integration from 0 to L. This is what? Exactly. This is the limitation of our, we are having here the length of our system to be is L, right? So we are talking about the integration because it's strain energy. We are integrating all the small parts here along this beam, right? Okay, so in this case, we're going to say m squared over 2ei times dx, it equals to the strain energy. From where we got this? This is, as I said in structural analysis 1, you can revisit this part, but it is important to understand that whenever we're talking about beams, so the straining energy, the strain energy is going to be based on bending moment. So this expression based on the least work method, which already we have explained before in the previous semester. Okay, so this is m squared over 2ei dx. Remember that our derivation parameter here, it's dx, because we are starting dx from here, right? This is x here. So we are starting our point, and this is, if you go back, this is why you can see this is x here. We say that this is the place of the redundant, and here this is the origin. Then we are going to measure any point across the beam with parameter x, location x, which is originating from B. Okay, so now this is the expression for the strain energy. Now what is the second step? Yes, we are going to apply the principle of the least work. According to the principle of least work, the partial derivative of strain energy with respect to By, which is our redundant, must be 0, as we have explained in the previous slides. That is partial, then we're going to take the partial u, partial by, we're going to put it here. So we put it here, partial u, partial by equal to the integration of the beam from 0 to L, this is across the length of the beam, and then the partial of m squared over 2ei. Actually, this partial, or the partial derivative for m squared over 2ei, if we are saying that m is considered to be a function of By, then it would equal to, by chain rule, it is going to be 2m over 2ei times partial m partial By, right? This is the m squared, then it is going to be 2m over 2ei as it is, and then I multiply by the chain rule, okay, using the chain rule. So this is partial m partial By, and this is what's happening here. This is partial m partial by, and then we have m. This 2 would cancels with this, then we're going to end up with m over ei, m over ei here. Okay, so this is the rationale for this equation. So if you look deeper into this equation, you're going to find that we have like two terms. We're going to integrate, because as you see, this is an integration, and we have two terms. One term is the moment are going to be derived with respect to by, and another term where that the moment only is going to work for us. Okay, I mean that going to be as it is, as a function of by. So the original function times the derivative of the function in terms of by. Okay, so we have this equation. Remember it. We're going to call it equation number 2. Okay, so this is equation number 2. Okay, so now let's using the x coordinates shown in the figure. We use this as our location parameter. This is the location parameter. Okay, we write the equation for bending moment. Now, as you remember that we need moment to be function of what? Exactly, of by. We want the moment to be function of the by. Okay, so we are going to write the equation of moment at any point here. Remember that we are taking the integration. This means that any point we want to know what is the moment at each point here, and then integrate it, right? So we're going to put it like this. We're going to say that the moment at any point here, let's assume that this is going to be the counterclockwise and its positive direction, positive sense of the moment. Then at any point distant with a distance x from B, then we are going to have the moment at this point is going to be by times x minus this portion of the distributed load, which is 1.6 times x over 2, right? So let's write it here in this equation. So it is by times x, and there is minus this part, which is going to be the distributed load. The distributed load is going to be 1.6 times x over 2, right? Because we are talking about any point here, so we have the distance here. So we're going to end up with 1.6 x squared over 2, which is this one. Okay, so now it is okay for us now. It is okay for us that we have obtained m as a function of the redundant by. And of course the parameter x, which is this x is going to be used, or it is going to be known for us as we know if we know the location, where the location. Okay. The next we partially differentiate the expression of m, with respect to by to obtain. So this expression, we're going to take the derivative of it. Byx, take care, we're taking the derivation with respect to by as our parameter, not x. Okay, take care of this. Okay, so x in this case, it is going to be known for us. Okay, x is going to be known because any place or any location, its x is known. However, by is our main unknown. Okay, so we're going to take the differentiation with respect to by. So here, by times x minus 1.6 x squared over 2. This is considered to be like a constant, so the derivation is going to be 0. And byx, the derivation is going to be x only. Okay, so this is what we have done in order to make. So now we have obtained m, and we have partial m, partial y. Let's go back. Do you remember that in our, yes, this is the principle of least work. We have partial m, partial by, one term. The other term is what? M itself. So we need to get both. From the example, we understood now how to get both. We got m, and then we got the derivation, which is partial m, partial by. Both of them are available for us right now. Okay. Now let's go and substitute in our equation. So by substituting the expression of m and partial m partial by into equation 2. Do you remember equation 2? This is equation 2 here. So we have this term and we have the m here. So just m equals to byx minus this blah blah blah, and partial m partial by equal to x, as we said before. So we are going to like multiply both here and we are going to put it into the integration. So ei, it is a constant, so we put it outside, and the integration from 0 to 30 because it is the length of the beam. X, which is partial m partial by, so put it here, and then this between the parentheses, it is the byx minus 0.8x squared, 0.8x squared dx. Now we are going to make the integration with respect to dx. Okay, so remember, go back. The differentiation here was with respect to what? By. Here, by, the main parameter for the derivation, or for, yes, for making the differentiation. So we reach this, and remember that in the denominator we are dealing with by, not x. Okay, but in the integration, whenever that we are integrating the limited integration, we are dealing with the main parameter here is x, because we are dealing now with x as the main parameter. Okay, for us it is x that is going to be our main parameter. That is, we are going to integrate each one based on the x of each location here. So x is going to be our main parameter. Okay, so now this is integration. You can say put this integration by parts. We have x and we have byx minus 0.8x squared with limited integration. You can do this using your own calculator. It is very easy to get the final value of this integration. Okay, and you can integrate it also by your hand. So by integrating, we can obtain that this is going to be 9,000 py minus 162,000 equal to 0. This is the main equation, which is one unknown only, one unknown, which is by in one equation, so we can obtain it easily. We can obtain by easily, which is 18k, and it is up, heading up because it is positive. Okay, then the remaining part is to determine the reactions of our equation here. So the reactions here, we know this now, is known. Then if we're going to take the moment here, then we can obtain ma, sorry. And if we're going to make the summation of f of y equal to 0, then we can obtain ay. And if we take summation of f of x equal to 0, we're going to find that ax can be obtained easily, and it's going to equal to 0. So from the summations of summation of moment equal to 0, from the three equilibrium equations, knowing by, we can obtain these three unknowns for the left side of the fixed support. Okay, so these are actually what we have done here. Okay, and this is as we expected. X was 0, ay 30, ma it is 180. Okay, again, I want to recap what I have explained in this example, to start from the beginning. First of all, okay, we look to this system. We realize that this system is one statically indeterminate. We have four unknowns and we have three different equilibrium equations. So we are going to use one of them to be the redundant. We chose by to be the redundant. Okay, then after that we are going to apply our least work method and the Castigliano concept. We want to get the strain energy as a function of the moment. Remember, as I said, we want strain energy to be function in the moment, and this moment should be function in our redundant, which is by. So we put this equation and we got it from, as we said, from chapter 7 of the book or from the previous videos in structure analysis 1. It is the integration from 0 to L for the entire length of m squared over TEI. This m is the moment at each point along the beam. According to the principle of least work, the partial derivative, if we are dealing, this is the strain energy, the partial derivative of the strain energy with respect to By must equal to what? 0. So we are going to take this strain energy, we're going to differentiate it with respect to what? With respect to By. Take care with respect to By, not X. Okay? Then we are going to make and put it like this. We have partial M partial By. So this is inside it. Sorry. So here we are going to see that if we're going to take the derivation, then it is going to be 2m, okay, 2m times over 2ei times partial m partial By, right? And this 2 would cancel with this, then we are going to end up with this part, okay, which is inside the integration. Then when we are going to integrate, we are going to integrate with x after that. Okay, so now this is m. We said that this is going to be the point of origin. X is going to be our location parameter. By is our redundant. Then we put m as a function of these two parameters here. Okay, and then we got the derivative with respect to By. So we obtained partial m partial By equal to x. Then we put it, we substitute in the main equation. We have m, we have partial m partial By, so we put m here, we put partial m partial By, which is this one. Then when we put them together under the integration, we obtain this equation, which is the integration with limited integration, x times between the parentheses equal to 0, right? This is a very simple limited integration. You can do it, and it is one equation in one unknown. Take care, we are taking the integration with respect to dx, our main parameter. Then you are going to end up with, exactly, because it's integration, limited integration, we are going to end up with the By to be the only unknown in this equation. We can obtain By, and then we can obtain the remaining reactions of the system. Okay, so this is what we have done for this equation, or for this system. Okay, now let's go to the next part, which is related to another example that we are going to deal with for the method of least work. The example is determine the force in each member of the truss shown. This is the truss shown here. We have a truss, okay? It is A, B, C, D, as you can see it. And there is a concentrated load here at the point D, heading to the right. And the dimensions are available for us. We have 16 feet, 12 feet between B and C, and the height is 12 feet. Actually, this is important to know, and EI is constant for each member. As long as we know the dimensions, this means that all the angles are available for us. So for example, if I say I'm going to call this to be theta angle, so theta is easy to be obtained. If we say that the theta or sine theta, for example, is going to be 12 over AD distance, or if we want to say that the tan theta is going to be 12 over 16. And here also we have another angle, which is, let's call it alpha, okay, between the horizontal and member BC. Also we can obtain this alpha angle easily. It is going to be 12 over 12, so we know alpha and theta. I mean that the dimensions and the configuration and the theta of the geometry is available for us, okay? Now let's go and try to get what is the indeterminacy of our system. What is the indeterminacy of our system? For the truss, whenever we are talking about indeterminacy, degree of indeterminacy, we have an equation which is already also, we have explained it before in the structure analysis one. It is, this equation is M, okay, whenever we are talking about M is the number of the members, that we have. We have here 1, 2, 3. So we have 3 members. Okay, we have 3 members. Plus R, which is the number of reactions. How many reactions do we have? We have 1 external reactions, 2, 3, 4, 5, 6. All of them, they are hinged, so each one of them is having 2 reactions. So we have 6 here. Minus 2J, which is the number of joints that we have. How many joints do we have? 1, 2, 3, and 4. So we have 4 points, 2 times 4. If you put it in this equation, you're going to find that we have one statically indeterminate structure. One statically indeterminate structure. Okay, so the truss contains one more member than necessary for internal stability. We're talking about the internal stability here. Therefore, its degree of indeterminacy is equal to 1. The degree of indeterminacy is equal to 1, as we have mentioned here with this small equation. Okay. Now, let's assume that we want to assume what is the redundant. Which one is going to be considered the redundant? We can't choose anyone. Okay, we can't choose anyone. And whenever that we choose the redundant, actually, we need to choose the one of the internal forces and the members. Okay, so our redundant is the internal force. So let us select the force FAD. So this member is going to be selected as our redundant, okay, to be the redundant. We will determine the magnitude of FAD by minimizing the strain energy of the truss with respect to FAD. Actually, why we said that the redundant is going to be one of the members, because if you know any member, you can get the reactions here easily. Okay, if you know the force in the member, you can get the reactions at the end of the support here. If you know this force, then these 2 reactions are going to be available for us, and we are going to obtain them easily, right? Similar here, this one is going to be 0, seemingly to be like this, and this one is we are going to have the 2 reactions easily if we could obtain the force in this member, which is member DC. So we can choose any member to be our redundant. We have chosen here FAD. Okay, so let's go back. So our FAD here is going to be our main redundant. Okay, let's go to the strain energy equation and let's see how we are going to deal with the problem. So the strain energy of a truss can be expressed as, remember that we are dealing with truss, not beam. So the strain energy based on the least work method is going to be F squared L over 2 AE. Okay, before, if you remember, for the M, which is related to the beams, it was M squared L over 2 EI, because we are dealing with the inertia. Here we are dealing with trusses, so we are replacing moment with force, axial force, and we are replacing the inertia with the area. Okay, remember this. We are dealing with trusses. We're dealing with trusses. Okay. According to the principle of least work, the partial derivative of strain energy with respect to FAD must be 0. That is, now we obtained U as strain energy. Okay. And then we need to get what? Yes, the strain energy derivative with respect to exactly our redundant. We have chosen our redundant to be FAD. So partial U, partial FAD is going to equal what? Take care, we are talking about summation, not integration. We're talking about deterministic summation, not integration. Before, in the moment, it was integration from 0 to L. But here it is different because we have different forces in each moment and each member, and we have a number of members. So here we have the summation going to be for 3 members, right? It is going to be for 3. We are going to repeat it for 3 members, for example, right? Okay, so take care of this kind of difference between the beam integration and the axial forces summation. Okay, so now we are dealing with summation, not integration. And then from inside, this can be the derivative here for this. It is going to be the same. It is going to be 2f, okay, times, this is 2f, this is the f itself, which is our force, axial force, remember, times this is 2f, and we are going to deal with FL over E A, and there is 2 here, right? So this 2 is going, sorry, this is, I'm talking about the partial now, so it should be like partial F, okay, so, okay, sorry for this, okay, so if we have this F, it should be 2F, okay, right, and times, which is the main one, which is times partial F, partial the main redundant, which is f of AD, and the remaining is going to be the same for us. The remaining was the same, which is 2AE. 2 would cancel with 2, and then we are going to end up with partial f of AD times FL over AE, right? So this is the how we could obtain the derivation from the strain energy expression. Okay, so now, as we have done before, we need first of all to get F, okay, we need to get U, strain energy, as a function of F, and this is already, we have done it here, and then F, we need it to obtain it as a function of what? Our main redundant, which is F of AD. So this is the sequence of our solution. Now we obtained U as a function of F. Now we need to go to the next step, which is F as a function of F AD, our main redundant. Okay. Now let's go to the second part. Then we need to express every axial force in this truss member. We need to express it in terms of our main redundant. This is our challenge. So the axial forces in members BD and CD, so we have BD and CD, should be expressed in terms of FAD. We know this is our redundant, we have chosen it. So the force here, the unknown, is FAD. But we want to express the forces in BD as a function of FAD. And we need also the force in CD to be a function of FAD. How we are going to do it? Okay. We are going to consider the equilibrium of joint D. So we're going to look to this point, which is point D. We're going to assume it. So we are going to take the equilibrium of this point, horizontal and vertical. Let's go to the horizontal, for example. Horizontal equilibrium, f of x equal to 0 at point D. I said before that this angle is theta, right? So, based on this, we have the horizontal component of FAD, which is FAD times cosine theta, which is this component, if we say this is the component here, minus 20, which is external force, minus 20, minus, there is a component from the member DC, which is going to be FDC times cosine alpha, the other alpha here, the alpha angle that I have explained before. So this is an equation, okay? This is an equation. As you can see, we have FAD and we have FDC. So FAD, it is our main redundant. And this equation only has FDC, so we can express FDC as in terms of FAD. So now DC, if you are going to substitute in the values for cosine theta and cosine alpha, we're going to obtain this value for the FDC, which is minus 28.284 plus 1.131 FAD. Okay, this is FDC from this equation, and we obtain it and put it here. In a similar fashion, we can obtain the vertical equilibrium at point D, and it is based on the summation of Fy equal to 0. So we're going to have the value of dB, right? So we're going to say, for example, if it's like F dB, which is going, let's assume it's going down, and the others also, they are going down because the components of FAD going down here. So let's assume it is plus FAD times what? Times exactly, this is theta, so this is going to be sine theta, so it is sine theta here, plus the component from the member DC. Take care that we have this value in terms of FAD, so we're going to put it plus here FDC, but you need to substitute with FAD here, times this component is going to be sine alpha equal to 0. If you are going to substitute here, you are going to find this is the FDB that is going to be obtained. You can check it by yourself as a second check for yourself. Okay, now we could obtain the values of, or an expression in each of the members in terms of FAD. We can obtain an expression for the members in each, the expression in the member in terms of FAD. Okay, now let's go now for our main equation for the strain energy. Remember that this is our strain energy partial derivative with respect to FAD. It equals to the summation of the partial derivative with respect to the partial derivative of the F with respect to the redundant times FL over AE. Summation means that we need to have like 3 values. So we're going to make it in a table, which is easier for us. So we're going to make a table, and this table we are going to put how many members? 3 members. AD, BD, CD. So this is the meaning of the summation here, which is, this is the meaning of the summation that we are going to have. We have 3 members. Then it seems that we have some constants that we need to, because we are going to multiply, so we need to put all the information for each member. So the length for each member in this table would be conveniently tabulated here. So AD we have 20, 12, 16.9. These are the values from the geometry. Okay. Then F is going to be the force, the internal force in each member in terms of our redundant. So actually the first one, which is member AD, the redundant, it is FAD. For BD, it is going to be the expression that we have explained before, 20 minus 1.4 FAD. Let's go back here, which is this one. And for DC, we're going to put this expression, minus 28 point blah, 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 right? So it is here, minus 28 point something plus, and at the end we have FAD. So now, member CD, it is a function of FAD. Member BD, function of FAD. Member AD, it is already the redundant. Okay, FAD. Then the next step is what? Get partial FAD. This term in our equation. So we're going to put this term now. So the partial FAD. We're taking this expression and derive it with respect to FAD. This is the derivation of itself, so it is 1. Then here, 20 minus 1.4 FAD, this means minus 1.4. That's right here. And here it is minus 28 plus 1.1 something FAD. Then this is the constant here, which is our derivation, 1.3. So we have now the expression for the second term here. The first term in this inside the summation sign. Okay. Now let's go to the multiplication part, which is we're going to multiply this term, okay, by FL. So we're going to multiply this term by F, and we multiply it by L. This times this term, then it will give us here. So just the three first columns are going to be multiplied, and the multiplication result is going to be reported in each one here. Okay, this one and this one here. Okay, that's it. What we're going to do now, simply we are going, the fourth column we are going to sum them up. These three we are going to sum them up. So whenever that we sum, we're going to find that this is minus 800 something plus 65 something FAD. This is one equation. Okay, then we are going to put, remember that we have AE here, we didn't use it, so we're going to put 1 over AE, the summation of this two terms, which is already here, and this summation is here. Okay, equate it with 0. Then you are going to find one equation in one unknown. FAD can be obtained easily. Okay, so this is the procedure for obtaining the redundant in terms of the truss. Now the redundant is available for us, right? It is available for us. This means that AD force, it is 13.4, right? This is the first member. Member BD, in terms of this equation, if we substitute in this equation by FAD, which is 13.4, we can obtain the value of the member BD, which is 1.136. So this is the second one. The third one, similarly, we can substitute in this expression and we can obtain the value, the force inside member CD, and which is minus 13.04. Minus 13.045. So we obtained all the forces in our truss members. Now, okay, going back. These forces are known for us now. We know them. Then all the reactions here and here and here can be obtained just by getting the horizontal and vertical components of each member. You can obtain the values of the reactions at each point. Okay, now we have now understood what is the flow of the least work method for our example based on an application related to axial force members only, which is the truss in our case. Okay, remember the main thing that we have only said it's a difference. We are using a summation sign, not integration, and in the same time here we are dealing with forces, okay, not moments, and in the denominator we are using area instead of the inertia. And then the differentiation with respect of the strain energy is going to be obtained easily. Our main idea is U should be in terms of F, and then F should be in terms of our main redundant that we have chosen. Then we're going to derive it with respect to the main parameter, and then we can continue our solution. As we have said, the best and the most convenient way is to use a table. As you can see here, it will make it very easy for you to obtain the values for each term in our expression main equation, and then we can obtain the summation and substitute in our main equation to obtain our FAD, our main redundant. Okay, I hope you understood it. It will. Now let's go to some in-class assignments and let's see our home assignment as well, and let's have an idea. In the in-class assignments, I'm going to give only like small hints. Mainly you should do it by yourself. Whenever that you see the equation or the problem, you need to work it out by yourself. After that, you can check the results from my slides. Okay, so you need to stop the video, working out the problem by yourself, and then check the results from the next slides. Okay, and I'm going to give the hints only about the solution. Now, this is the first in-class assignment. Method of least work in-class assignment. Determine the reactions. We want to get the reactions using the method of least work. It's a cantilever here. As you can see, we have 1, 2, 3 unknowns, and we have one unknown here, right? And we have a distributed load here. Seemingly, as you can see, we have like, okay, 4 unknowns, so we can choose one of them to be our redundant, because we have our 4 main unknowns minus 3 equilibrium equation, means that we are dealing with only one statically indeterminate system, and we have to use only one unknown. Okay, one redundant. We have to use one redundant. Okay, so now I think that you can start with by to be your redundant, and you can continue this problem. So now I strongly recommend for you to stop the video here and work this example using by as your main redundant, and work and let us know what are by, what are the by and the remaining reactions here. Okay. I will suppose that you already have done what I have said, that you worked out by yourself, and this is only some hints about what you should do in the in-class assignment. So first of all, we have chosen by to be our redundant, as we said here, and we have chosen point C to be our origin for the integration. So first of all, we need to get u as a function of the moment, first of all. Okay, and this is already done. We know it will, that u is going to be, as we said, it is m squared over 2ei. This is what we have said before in summation from 0 to L. So this is known for us. Now the second step is what is m as a function of our main redundant, which is by, and this is what we have done here. So the equation here is going to be given for us. This is the m here. So we have like 2 spans, so just we make a small table here for 2 spans, CB and BA, CB and BA. We put the x coordinate as the origin is C, from 0 to 7, and from 7 to 14 for BA. Moment here means that the moment that is going to be used for expressing by, which is for member CB, it is going to be any moment here. If we start from this point, any moment is going to be what? Yes, it is the distributed load, which is 15, right, times x times x over 2. This is the moment in this case. 15 with this cancelled, it gives us 7.5. Okay, and 7.5 x squared, and it is minus because it is making moment down if we use this sign convention. So we have minus 7.5 x squared, as I have said here. In a similar fashion, we can obtain an expression for moment for member BA. The ranges is going to be between 7 to 14 based on x, because x started from here, so we're talking from x7 to x14. How we can obtain? We have the values here. The same contribution from the first part, which is minus 7.5 x squared, plus the contribution from the from by. Take care, the first part here, this one, it is the contribution of the distributed load along the whole beam. So it is the same here. Okay, minus 7.5 x squared plus the moment coming from by, it is by times this distance, which is x minus 7, right? X minus 7, which is spanning from here to here, from point B to point A. Then the partial derivation for this one, we do not have any value for by, so the partial m partial by here is going to be 0. However, this one we have by here, so we're going to have x minus 7. This is our partial m partial by. So now we can obtain m as a function of by, which is this column, and then we can obtain partial m partial by, as you can see in the second column here, in this column. Then you are going to put it easily. We are going to have two terms actually. One term for CB, which is from 0 to 7. So we're going this equal to from 0 to 7. The integration of what? Yes, it would be 0 here because we have partial m partial by 0. Okay, so the term here is going to be 0 for the first part. So this part will not contribute anything for us. The second part, which is plus the summation from 0 to 14 here, 7, from 7 to 14, it is from 7 to 14. Then it is going to be x minus 7, which is partial m partial by, times this is m, which is this expression for m, dx. This is a simple limited integration from 7 to 14 expression. You can do it by yourself or by your calculator, and you are going to obtain by easily to be 223.125. I hope that you have obtained this value when you worked this example by yourself. Okay, so this is the first in-class assignment. This is the first in-class assignment. Let's go to another in-class assignment, okay, which is a little bit combining the two concepts that we have explained before. Okay, so here in this system we are having like two components, two elements. Okay, so actually the example is determine the tension in the cable using a method, the method of least work. So we have a beam which is having a fixed support at point A, and at point B there is a cable here which is, we call it CB. This is the cable here, and this cable, it has area of 0.5 inch squared, and the length of this cable is 5 feet. The main beam is having a distributed load with 2 kips per foot, and the inertia of this beam is 500 inches to the power 4. And the length is 15. E is considered constant in your calculation. So we need to obtain the tension here. First of all, let's go through the putting first things first. What are the main redundants or the main unknowns that we have? We have like 1, 2, 3 unknowns here because this is fixed support, and we have the cable tension here, which is T. This is another unknown. So we have 4 minus 3 equilibrium equation means that we have one statically indeterminate system. This suggests for us that we can use our redundant to be one of these unknowns. It seems that they are asking here requiring tension, so we are going to use T, the tension in the cable, as our main redundant. Well, that's very nice. Remember well, the strain energy that we are going to talk about here, it is coming from two parts. One part related to the beam, which is going to be controlled through the flexural straining actions due to moment, and the other one, or the other part, is coming from the cable, which is controlled by what exactly? The axial straining actions controlled by the T, the tension force in this cable. So we have two parts. We have M, we have beam, we have cable, we have M, we have T. So we are going, M means that we are going to deal with what? Some integration, right? And T means that we are going to deal with what? Yes, summation. So take care of this, that we are going to have two of them. We're going to have two of them. After explaining these hints for the in-class assignment, I strongly recommend for you to stop the video now and try to work this example by yourself. After that, you can go through the solution that I'm going to show in the next slide and verify what you have done. Okay, now let's go to the next and the solution of this method. Yes, here. This is the method of least work in-class solution. So we are going to assume that our redundant to be T, as I have said before. Then we are going to have two parts here. Partial strain energy, partial T, our redundant, is going to be axial part, which is partial F, partial T, FL over AE, and another part which is what? Integration, as I said to you. Partial M, partial T times M over EI. This part, flexure, it is related to the member AB because it is beam. And this part, which is the axial, it is related to the member CB because it is axial force. It is only related, or we can deal with it as an truss member. So for the cable BC, F, it is the redundant, is going to be T. And partial F, partial T, which is here that we want it, this term, it is going to be 1. For member AB, M is going, in terms of T, is going to be, yes, T times X, if we take B to be our origin, and this is X, so the moment at any point along this beam AB is going to be T times X minus the distributed load times half of the distance, right? So it is going to be T times X minus 2 times X, which is the distributed load, 2 times X, times X over 2. 2 cancels 2, and then we are going to end up with X squared, and there is a minus here. Then partial M, partial T is going to be what? X. Take care, this is Tx minus X squared. So our main variable in that derivation always is what? Our redundant. So we have T as our variable, X is a constant, and then of course minus X squared is another constant. So our partial derivative with respect to our redundant is going to be X. Partial U, partial T, it is very easy now. We can substitute in our main equation with the number of, it's only one member, which is CB. We are dealing with it as a truss member, so you can substitute easily here, plus the integration from 0 to 15, which is the length of our beam, and this is the expression inside it, which is X times M, which is Tx minus X squared. It's similar here. This is 1 times also here partial F, partial T, FL over EI. So it is similar to our, take care, this 0.5, it is the area, I guess, which is already given in the previous one. And this T, it is this F, which is FL, and we have L, which is 5 meters. And then over EI, this is E, and this is EA. Okay, so now we have everything, one equation in one unknown. We can obtain T easily. We can obtain T easily. Okay, I hope that you have obtained this example, this result when you worked it out by yourself. Okay, now after having these, you are trained well now. You are ready to go through the home assignment for today's lecture. Then this is the home assignment. Okay, sorry for this. You are going to have 2 examples, okay, or 2 home assignments. This is the first one. Okay, fixed here. There is support here. 3 unknowns here. You can take by as redundant, and you can continue by yourself. Okay, determine the reactions using the method of least work. Okay, so determine all the reactions based on the least work. And the second assignment is going to be this truss member. So determine the reactions using the method of least work. Okay, we want the reactions. As you see, we have 1, 2, 3 reactions, outside reactions, but check what is the indeterminacy of the internal forces of the system here. And I recommend for you to start with FBC, this member, the force in this member, take it as redundant, and then continue solving your system. Okay, I hope you understood well what I have said today. The method of least work is very nice and very easy, simple to understand and simple to implement. I think that we have gone through everything for the least work method, and I hope that to see you in the next lecture. Thank you and see you.